morning everybody. So, in this episode of chemistry class, I will be talking about you on redox reactions. This particular topic we will discuss because these redox reactions are mainly concerned with two things. One is the reduction process and another is the oxidation process. And studying this has serious implication on several aspects of activities, particularly when we study from our early school days that the process which we know is the burning of say fossil fuels. So, burning means in presence of oxygen. So, what does it mean? So, that particular type of burning we can consider that some material A is there which can be oxidized in presence of O2, giving rise to our AO2. So, if our fossil fuel has carbon present in it, so carbon can be oxidized very nicely by forming its corresponding oxides, and that releases some good amount of energy. So, that is the requirement for the burning process. But what about these two things, that means the corresponding reduction process and the oxidation process, because these two processes are starting from this burning of fossil fuel to another process which is the corrosion of metals. So, most of these cases we will find that they are very important in terms of the corresponding available metals, whether it is a typical material where the metal is present as some iron rod, iron pipe or something, and we can talk about the environment where the environment can be correlated to the presence of this oxygen. So, the corrosion of metals basically known as the corresponding degradation of the corresponding metal. Metal means it is in the metallic form, it is in the zero state, zero oxidation state. So, typically what we say that in the case of this, that means the burning of fossil fuel to the environment where corrosion of metal takes place, we can have both these two processes of reduction as well as oxidation. From very early days of photosynthesis, we know another example. And from our early school days, we know that is a typical process where plants do synthesize something for us involving carbon dioxide and water molecules. So, this I will come later on, where we will find that how these two species can be useful for the formation of the glucose material, which is C6H12O6 with the elimination of molecular oxygen. So, in this process, if we balance it also, is the 6 molecules of CO2 and 6 molecules of water molecules will give rise to our C6H12O6 plus oxygen, which is 3 in number. So, in this process what we see that this is again a very simple process in terms of its oxidation and reduction, where CO2 and water molecules are taking part actively to give us the corresponding C6H12O6, where the CO2 molecule is undergoing reduction and the water molecule is undergoing oxidation. So, in this very simple process of photosynthesis, what we know from our early days of schooling, that there also these two reactions, that means the oxidation and reduction reactions are involved, and this is involving formation of some energetic molecule, because this particular thing, that means the glucose molecule, which can give rise to the carbohydrates, which are our main source of energy. So, there we find that this particular oxidation reduction reaction can take place, which is not similar to that of our burning of fossil fuel or corrosion of metal ions or metals, where addition of oxygen can take place. So, if we come back over here, where the addition of O2 to A giving rise to AO or AO2 type of thing. So, anywhere the addition of this O2 to an element or compound, if we can have such as the species we can get is Fe2O3, Fe3O4 or some other metal oxides like ReO3, titanium dioxide, zinc oxide, magnesium oxide. So, these are the very simple example of this addition of this O2 or more to a metal, where you have iron, you have rhenium, you have titanium, you have zinc, and you have magnesium. So, these are basically, sometime we will find afterwards that these are also the corresponding ores and minerals what we get on the earth crust. So, the available metal as the metal ions is getting reduced to the corresponding metal, and this undergoing some kind of addition reaction of oxygen for coming from the environment to give us the corresponding oxides. So, addition of O2. So, to these elements and compounds can be termed as the corresponding oxidation reaction. So, what about this particular thing, what we can find from the periodic table for this particular course is the class unit of 1108. So, and I am Devashish Rai talking about you to the redox reactions, and this particular one can also be correlated to the rust in an iron oxide. So, just now what I told you about the formation of Fe2O3 is the corresponding iron oxide, and this iron oxide can be formed from the combination of iron metal and O2. And what we have learned so far, that the addition of O2 to an element or compound or a metal is termed as the oxidation. So, what type of this particular addition is that if we just go into the periodic table, the whole periodic table, if we little bit recall back, that on the left hand side or the lower part we have the corresponding electropositive elements, and on the upper right hand side we have the corresponding electronegative elements. So, these are the corresponding electropositive elements, and these are the corresponding electronegative elements. So, these reactions basically what we can consider, that what is oxidation. We can consider this oxidation, therefore, that O2 will be here, somewhere here, oxygen is here. So, is an electronegative element. So, addition of this electronegative element is also known as oxidation, and reduction means the corresponding reduction means, therefore, the combination of less electronegative or removal of electrons. So, here in case of oxidation we have the corresponding removal of electrons, and here we have addition of electrons. So, these two processes follow side by side, where you find that in a particular redox reaction, which is nothing but the reduction as well as oxidation process, which involves both these processes. And initially what we understand that fundamentally the redox reactions are a family of reactions where we consider about the corresponding transfer of electrons. So, how do we know about the corresponding transfer of electrons? So, the same oxidation process can be defined as the removal of electron, loss of electron, or another term we can use is increase in corresponding oxidation state. So, here we see that the corresponding oxidation state of iron, which is in the elemental state, is metallic iron is in 0. But in this particular case where you have the Fe2O3 formation, where the oxidation state of iron is +3, this iron is 0, sorry, this oxygen is 0. So, this is both of these two are in the elemental state and has gone in this particular case to O2 minus. So, increase in oxidation state, that means the oxidation state is changing from iron 0 to iron 3 plus, that means Fe 0 when it goes to Fe 3 plus is the typical oxidation process, and we see that the corresponding O2 is gaining electron and gain of electron, and in a negative direction it is the decrease in oxidation state. So, it is the corresponding decrease in oxidation state. So, O is going to O2 minus, which will be our reduction. So, these two processes, that means the oxidation and reduction reactions when occur simultaneously, that means in this particular case it is the loss of electron. So, it is minus 3 electron. So, loss is 3 electron and this is plus 2 electron giving O2 minus. So, whenever we find that in a particular reaction there is a loss of electron, obviously that electron can be taken up by some other species which will be responsible for its reduction by gaining of electron. So, if we can go for some kind of burning of fuel as we are talking about, so some example is also that we can have the cannon fire. So, if we can have the burning of carbon, which is the regular fuel for the typical burning process, but if we get or if we use some oxidizing agent. So, such as one typical well known oxidizing agent is our potassium permanganate. So, which can oxidize some other species where manganese is present in +7 oxidation state, and we all know that the manganese can have variable oxidation states from the elemental manganese, which is 0. So, this particular reaction is nothing but if we take KMnO4 powder and then we just sprinkle that powder on a burning mixture of H2O2, which is hydrogen peroxide. So, the reaction basically what we are thinking of in a different way for the typical fire. If we consider that there is some firing or there is some burning process, so what will happen therefore? That means this particular species, that means the KMnO4 will be available for its reduction reaction, because the manganese is already in the +7 oxidation state. So, it will go down to +4 oxidation state in MnO2, and this hydrogen peroxide will be available for the production of O2. Then we can have also water will be there from the reaction and the hydroxide ions. So, in a single shot there is the evolution of this particular oxygen, so which is very much localized, So, this localized evolution of O2 can accelerate the burning process of what? We are calling it as a cannon fire, and where this H2O2 is there with some fuel material, say we have taken this H2O2 in ethanol, C2H5OH or ethyl alcohol. So, that ethyl alcohol will be burned therefore, and the presence of this oxygen accelerates the corresponding burning of this E2H, and there is some burning process which will be responsible for this burning of this ethanol. So, again we find that this particular one, and we will just now carry on this one, that how we get this O2 like that of our photosynthetic reaction, where this O2 is coming from your H2O2 or this water or hydroxide ions are coming from this H2O2 hydrogen peroxide molecule, that we will see. So, the rusting process, what we are just seeing here, that is rust is an iron oxide usually red and formed by the redox reaction of iron and oxygen in the presence of water or moisture, and it consists of hydrated iron 3 oxide. So, just now what I told you that is Fe2O3, and if it is hydrated, so some number of water molecules will be attached to it, and this will be red in color. So, the formation of this starting from your iron and the atmospheric oxygen simultaneously tells us that we can have the corresponding oxidation as well as the corresponding reduction process. So, if we have O2, which is a very important reaction that we all should know, that O2 also we require for the burning process of our food material. For our survival, we also need O2 molecule for burning the food material what we consume for getting the energy. So, in a typical reaction in terms of that electron transfer, where 4 electron can be transferred to this O2 molecule, and the presence of this water molecule is nothing but the source for the corresponding H plus to give you the corresponding hydroxide ions. So, the hydroxide ions getting it from the O2 molecule is a typical reaction where we get a 4 electron reduction process, and if we have more number of H plus proton over here, so we can produce more number of water molecules on the right hand side. What does it mean therefore? That O2 can be effectively reduced to water molecule. So, that is the typical reduction process when we go for burning of the corresponding food material. So, if we have the glucose molecule which is our C6H12O6 which is getting oxidized by O2. So, O2 will take up these electrons to reduce it to either hydroxide ion or to water molecules. So, this we have seen that at the initial stage this iron is initially oxidized to Fe2 plus. The oxidation process is the ferrous iron oxidation process with the removal of 2 electrons, and this on further oxidation with this O2. So, O2 is playing some double role or dual role. This O2 is utilized to oxidize further this Fe2 formed over there for the rust formation. So, all these electron transfer reactions are pretty complex, and particularly the very most important molecule is the water molecule. So, what we know from our early days that the corresponding electron transfer reactions we do not study much for this water and O2 molecule, and intermediately we just get the formation of the hydroxide ions, and we can have the typical water molecule over there. So, these always involve some transfer of electron. So, if we consider that O2 is utilized for the reduction process, so it can take off electron. So, O2 we all know that is a very standard bonding picture of O2 is a typical diatomic molecule. So, if it can take one electron, it can go to O2 minus. So, that species we all know, and if it again accepts another electron, it will be O2 2 minus, which is nothing but the peroxide anion. So, we will find that there will be a change in the corresponding bond order from a double bond nature or the character or between OO, it will be a single bond character in O2 minus, and then again a single bond nature of full size is for the corresponding peroxide. Then if we find that there is some OO bond cleavage, the cleavage is there, and this can give rise to the corresponding formation of HO minus, the hydroxide ion. So, in this way the electron can be accepted by this O2 molecule, and this O2 molecule will be responsible for the formation of your hydroxide ion. But in this particular case, in the third reaction where 4 Fe2 plus O2 is forming 4 Fe3 plus and 2 O2 2 minus. So, this will basically give us something where this oxygen is utilized for the oxidation of the ferrous ion to the ferric ion, and this O2 is now converted to the oxide ion. So, is another form of oxygen which is forming from the dioxygen molecule to produce the oxide ion, which is present in water molecules, say for a very simple reaction. So, if we just think this particular thing, the one form of the periodic table where we see that this typical electronegativity values. So, periodic table if we see in terms of the electronegativity values in Pauling scale, we find that in the case of this periodic table we have the cesium, which is classified as a corresponding typical electropositive element. So, this sodium, potassium, rubidium and cesium. So, cesium will have a corresponding value of 0.79. So, in the periodic table the list electronegative element and the most electronegative element we can have. So, this is cesium having a value of 0.79 in the Pauling electronegativity scale, and the most electronegative one is the corresponding fluorine, which is 3.98. So, this particular species, so this electropositive or the less electronegative element will be oxidized very easily, and it can give rise to the corresponding electron transfer reaction, and that electron transfer reaction can be supported by the presence of the corresponding most electronegative elements on the upper right hand side of the periodic table, such as oxygen, which is 3.44, or the fluorine, which is 3.98. So, in a particular case of this reaction, say just now what we are seeing, that the formation of hydrogen peroxide, which is a covalent molecule. So, the covalency of this particular molecule, that means the hydrogen peroxide having OO bond and HH bond, what you see that in the covalent bond formation we have only the partial charge transfer. So, if we have partial charge transfer and if we see the difference in the electronegativity values between hydrogen and oxygen, one is 2.20 and another is 3.44. So, the partial charge generation on hydrogen and oxygen will be delta plus and delta minus by sharing of the electron pair between the bond of oxygen and hydrogen. In a similar fashion, the other bond, the other OH bond will also have a delta plus charge and a delta minus charge on oxygen. So, this is a situation where we can have the assignment for the corresponding oxidation state of this hydrogen and oxygen in this molecule compared to that of our water molecule. So, water molecule is also a typical covalent one. So, where we have this delta plus and the delta delta minus charge on this oxygen. So, these are typical covalent molecules where we have only partial charge due to the difference in the electronegativity values of these two elements. So, the electron pair which is holding these two atoms are shifted towards the oxygen side, that is why a negative charge is being developed. Since hydrogen is losing its share for this electron pair, a corresponding delta positive charge is developed on this hydrogen. But from this particular situation, this is due to the partial charge separation, we cannot talk in terms of the corresponding oxidation state. But here in this class, we are only interested to assigning the oxidation state of these species, these elements. So, how we get these corresponding oxidation states of these elements or the corresponding hydrogen and the oxygen is that we just consider that this particular charge separation continues and this particular charge separation is giving us to something where we can have hypothetical ionic bond, and that hypothetical ionic bond will lead us to a complete charge separation. So, a complete charge separation will give us something where H OOH is there. So, it will be 1 minus, this will be also 1 minus, this is 1 plus and this is 1 plus. So, in the hypothetical ionic bond formation, whether it is for the hydrogen peroxide or the water molecule, we will get that a complete charge separation can take place, and this H which has already acquired a positive charge, 1 unit positive charge, can remove from here as H plus. The other hydrogen is also of same character. So, it will also be lost from there by losing as H plus. So, what we get? We get the corresponding ion, that means O2 2 minus, which we already seen here that due to the electron transfer. So, complete electron transfer will also give us to this particular species, which is O2 2 minus with 2 H plus. So, this assignment of these corresponding charges on the molecule, which can be a covalent molecule, but if we assume that a hypothetical electron transfer can take place where complete electron transfer can take place from the pair of electrons shared for this covalent bond to the most electronegative or the higher electronegative side, we get this particular species. So, this particular thing is the assignment only typically based on these periodic table based on the Pauling scale. So, if we take another example, that means this fluorine, which is 3.98 and which is on the upper extreme side, which is red in color also. So, this fluorine, when it is forming some bond with one compound, what we all know that which is OF2. So, how this particular charge separation can take place? So, the difference between oxygen and fluorine is there, which is 3.44 and 3.98. So, which is therefore, the separation will give rise to a negative charge separation on F minus. So, F minus will always be there as a negative charge and this O will be O2 plus. So, though it is very unusual that we can have a oxygen center present in OF2 molecule, which has acquired a 2 plus positive charge, which is quite unusual, but since it is attached to the fluorine atom and where the charge separation is of different nature and fluorine will attract the electron pair of this OA bond towards fluorine, and it acquiring a negative charge. So, O will be acquiring a O2 plus. So, that is why this acquiring of positive charge on this particular species are not unusual. What we have seen that this O2 minus. So, if we just know a little bit about the corresponding molecular orbital picture of this diatomic O2 molecule, we know that we can push one electron to the molecular orbitals and we can generate the species which is O2 minus, which is our the corresponding superoxide anion. So, superoxide anion can be formed. So, this is our superoxide anion. So, this superoxide anion is formed, but the 2 electron transfer what we get from there is our this one which is forming as O2 minus, which is the corresponding peroxide ion. But if our O2 is going for some kind of electron loss from the molecular orbital, that means minus 1 electron. So, like this OF2 species, it can also acquire some positive charge. So, that will be O2 plus. So, this O2 plus, which is the oxygenyl ion, which can have some existence also. So, this O can therefore have different oxidation states. So, we can level for this O, because if we consider that O is the standard element where the other compounds are forming by combination with the other elements like hydrogen, like fluorine, like Cl and all other. So, different oxidation states, that means the possibilities of all these oxidation states are therefore important in assigning the particular oxidation state of oxygen as well as the other species or the other elements which is attached to this oxygen. So, based on this Pauling scale, if we just consider that what we get the differences. So, Pauling scale electronegativity can tell us little bit about the corresponding chemical bonds. So, there is a error is because LINUS, this is the Linus Pauling is LINUS. Okay. So, there is the difference in electronegativity. So, if we consider that the species, that means the bond is forming between A and B, and A has a particular electronegativity from the scale, and we just consider the corresponding difference. So, now the difference will tell us the corresponding nature of the corresponding bond. What we have seen here also, that when we have the covalent bonding in water molecule or hydrogen peroxide, we consider that there is a charge separation, a small amount of charge separation. So, if the electronegativity difference is not much, we get only the delta plus and delta minus charge separation. So, what we get, we can tabulate this as in this particular table in this slide is telling us that you can have the non-polar covalent bonding over here. So, this nature of this bond is therefore non-polar. So, when this hydrogen peroxide or water molecule is present and it is not doing any other reaction basically, that means some external agent is not added, they remain as non-polar covalent bond. But if we consider that some reaction is taking place, some A is reacting with water molecule itself, then this particular non-polar nature will not be there, and that non-polar nature will be destroyed, and we can have the complete electron transfer giving rise to a corresponding polar covalent bond or ultimately release of this H as H plus, which is a typical characteristic nature for the removal of this H as the corresponding ionic bond, which we find in case of HCl. HCl we all know, if we assign this is 1 minus, this is 1 plus, the oxidation state assignment, but this is a typical gas molecule. So, this gas molecule has a covalent nature because this electron is shared by this one ardent pair electron on the chlorine atom, giving rise to a covalent bond. But when we dissolve it, so if we have HCl over this HCl is A and it is reacting with water. So, this particular one will give rise to some reaction. So, where this reaction is giving rise to the corresponding removal of this Cl minus from HCl unit. So, this HCl which is gas which is dissolved in water and we get an aqueous solution of HCl. So, aqueous solution of HCl will give rise to Cl minus and it will be removed as H plus. So, that H plus will be accepted by this water molecule giving rise to H3O plus. So, this typical nature what is originally present as a nonpolar or a slightly polar bond for this HCl when it is reacting with this water molecule is giving rise to a typical ionic type of bond which we find in case of sodium chloride say, because when sodium chloride is dissolved in water we know that it can dissociate like Na plus and Cl minus. So, the nature of this thing can be changed if we go from one particular reaction to the other like that of the difference. So, if the difference is falling within a range of 0 to 0.5 we get a nonpolar covalent bond. If it is 0.6 to 1.9 we get a polar covalent bond. So, charge separation is appreciable, and if it is above 2 it will be a ionic bond. So, if we consider that you have a sodium and chlorine. So, the sodium chlorine separation will be above 2 and you have a typical ionic bond which is present in case of sodium chloride, and assignment of the oxidation state is also clearly defined as Na as Na1 plus and Cl as Cl1 minus. Okay. So, this particular type of bond. So, dependence of bond type is basically governed by two parameters. So, means we are talking in terms of the electronegativity. So, the electronegativity difference is there and the average electronegativity. So, if these two parameters are the controlling parameters, then we can define this particular nature of these molecules as whether it is ionic compound or a covalent compound. So, in case of this ionic character like which is present in NaCl is governed by the partial charges of the bonded atoms, and this particular character is there if we have a typical change, but another character we consider here also is the metallic character. That means, if we have both of them as sodium. So, if we have sodium and side by another sodium is also there, that means the metallic sodium. So, there again you do not have much difference in the corresponding electronegativity. So, we get something, but which is not of the type which we get in case of Cl2 or H2, the hydrogen molecule or the chlorine molecule. But here this typical metallic character will be governed by highest occupied molecular orbital. So, we have to take the help of the molecular orbital picture of these, and the gap between highest occupied molecular orbital and lowest unoccupied molecular orbital will give rise to the band gap, and that band gap will tell you some metallic character. So, conduction band to valence bands are formed, and those bands will typically go for a metallic bond. So, is of different type, and we basically see that the nature of the dependence allow the rationalization of the variation of the bond type. So, we see how these different bonds are basically forming when we just allow the corresponding formation of the different types of molecules. So, we see some of these examples. So, is basically a triangle, a ternary plot, and this triangle basically is nothing but examples of some binary compounds or a ternary compounds like magnesium hydride or lithium hydride, where we consider that where we get. So, you have this particular one, that means the difference as well as the average electronegativity values. So, these electronegativities values we typically dictate us where we have this F2, H2 and Cl2, where this difference in electronegativity, the delta values on electronegativities are 0, but the corresponding average electronegativity is high, which is in the range of 2.5. So, that is why these F2 and all other species are close to the covalent nature, and this particular covalent nature is also valid for our O2 molecule and our Br2 molecule also. So, if we go along this line, we see that just now we have seen that the species like OF2, so similarly other binary species are also forming, and we get that is water is there which is in between. So, you have some covalent nature of this water molecule, but you have something where some charge separation is there, and that charge separation is basically giving us some example where we get that partial charge separation will bring this, because your average value is a little bit high, which is in the range of 2.2 or 2 in the range of 2, but the difference is small. So, you have some charge. So, as we move from this line, from this covalent to the ionic side, we will find that the nature of these molecules are changing as we move from F2 to CSF, the cesium fluoride, which we all know that is the typical ionic compound. So, this cesium fluoride will be there, which is very much similar to that of our sodium chloride. So, what we are changing? We are changing the presence of the other elements. So, other elements, as we change, we move from there to the other side. So, assigning this from the difference in corresponding electronegativity values are sometimes very straightforward, but if we find that is not always so simple, if we get some species where we can have the species like this BRF and CLF. So, this particular thing, that means one more example is our CLF and one is BRCl. So, if we look at the corresponding values for electronegativity, we will find, because already we have seen side by side that how you just consider the HCl or HBr. So, this will be 1 plus, this will be 1 minus. Similarly, for HBr also it is 1 plus and 1 minus, but what about this? So, in this particular case, so it is CLF, so this will be 1 plus. So, it is not 1 minus, because you have electronegativity difference from fluorine. So, fluorine will acquire the 1 minus charge. So, these are the typical interhalogen compounds. These interhalogen compounds will tell us the corresponding charge separation as well as the assigning of the oxidation state on fluorine on chlorine. Similarly, for BrCl also, the Br will be 1 plus and Cl will be 1 minus. So, that assignment we always should keep in mind the corresponding delta values of all these things for assigning the corresponding oxidation states. So, this particular bond also we see that these are typical corresponding intermetallic species. So, intermetallic species are all metallic in character, and in case of metallic thing, that we, since we do not have any separation, the electronegativity separation is not much. So, we will not find any charge separation or are localized in the different bands what we see for the corresponding conduction band and the valence band. So, what we see that in the case of water oxidation, just now we have seen that water is getting oxidized for the formation of corresponding O2 molecule, and that particular O2 molecule is our corresponding oxidation reaction. So, at the same time, if water is getting that particular electron through the oxidation of water for the production of this O2, what we get for the photosynthesis also, that something should be present over there which can consume these electrons which is produced in the first step for the oxidation. So, this can be consumed by the corresponding protons or H plus or the hydrogen ion, forming the hydrogen gas or the hydrogen molecule itself through reduction process. So, overall the reaction is nothing but for the water oxidation reaction we must have the production of hydrogen, and we must have the corresponding O2 also. So, this we also consider or so call as the water splitting reaction. So, that particular water splitting reaction is another reaction where we get this O2, that means the production of O2 for the photosynthesis, but in case of photosynthesis hydrogen production is not there, because this hydrogen, the corresponding reduction equivalent, is consumed by the CO2 molecule, and that CO2 molecule will be responsible for the production of glucose. So, this particular process what we see there, which is a natural process, and we also considered is as a photosystem 2, and it is provided by the plants. So, this particular reaction is providing us protons. So, these protons are forming and the electrons for the photosynthesis process and release oxygen to the atmosphere. That is why we get the release of oxygen. So, the very basic reaction for our survival for the photosystem 2 or the PS2, what we consider is that there is a typical oxidation reaction what nature does for us. So, in this particular class of this redox reaction, what we see that we can have some material and that have the ability to oxidize the other substance and is said to be oxidative, that means it can oxidize the other things. So, it is the oxidizing agent or oxidant or oxidizer. So, what does it do? It does basically it removes electrons from the other system or the other substance. So, when it gets electron, then that oxidant will be reduced itself. So, thus it itself is reduced. So, if we get some example of oxidants, so you should also characteristically know, because in our next class we will see that if we get some species like say MnO4 minus, that means it is the anion which is derived from potassium permanganate, which is KMnO4, or some other species, the metallic species or the metal oxides like osmium tetroxide, where what we have just typically we can assign the corresponding oxidation states that Mn has, the chromium has, here also the chromium has, and also that is typical osmium has. So, in all these cases what we see that if we have osmium tetroxide, we all know that osmium is present in the iron group. So, iron, then we have ruthenium, then we have osmium. So, is possible that you have this a tetroxide is there, and side by side we have also CrO3. So, if we assign these are oxides, so these oxides are there. So, quickly we can assign the oxidation states for these oxides as O2 minus. So, obviously, the chromium will have a hexavalent and osmium is also 8 plus. So, these oxidation states what we reach there starting from chromium 0 or osmium 0 is not so easy, because by the loss of 6 electrons over here and 8 electrons over here will take us from osmium 0 to osmium tetroxide. Similarly, from chromium 0 to chromium trioxide. So, these are the species which have high oxidation states. So, what does it mean basically? Because this is the highest possible oxidation state of chromium, this is also the highest possible oxidation state of osmium, and we do not have any electron on chromium and any electron on osmium. So, we are not able to go beyond these oxidation states. So, the other thing it can do, it can very easily accept electrons. So, it can accept electrons, so plus electron. So, it can function as a good oxidant and itself is reduced and go down to the lower oxidation state. Similarly, so species having high oxidation states and other species what we are just now discussing in terms of the electronegativity values, your O2, your F2, your Cl2 and Br2. So, that can gain extra electrons. So, these are also oxidizing agents or oxidants. How? Because these can also accept electron. Already we have seen just now that O2 can accept electron, it can accept 2 electrons, giving rise to O2 2 minus, or it can break to hydroxide ion or the water molecule. Similarly, fluorine, chlorine and bromine can also accept electron to move to fluoride, to chloride, to bromide. So, electronegativity will tell us that these can easily accept electron, and they are also good oxidants because they are easily reduced. So, we find that in this particular case that the reverse one, the other process which is the opposite of these oxidants. So, these are all reductants. So, reductants are what? Reductants are basically therefore very easy to see from the periodic table on the left hand side or the left hand lower side of the periodic table, that if we have the electropositive metals like lithium, sodium, magnesium, iron, zinc and aluminum, that can donate electrons easily. So, if we know that some of these metals these are responsible for some reaction which are violent in nature, because we know that sodium can be violent if it reacts with water, because it immediately gives rise to the corresponding burning process of this water, and it can immediately go for the corresponding reduction reaction, and it gives rise to the corresponding electrons to the other species. So, can donate electrons readily. So, if we just think of the corresponding zinc also, and zinc in the elemental state or the metallic state, we can consider as the zinc is a typical species and direct reaction we can have. So, the laboratory example of this particular reaction, this iodine, we all know that iodine is a solid one also, black particles, iodine solid. So, if we consider in terms of the corresponding redox reactions between zinc and iodine, we see that this particular zinc is the reductant. So, it will basically give rise to electrons. So, the electron flow will be taking place from zinc to iodine, and directly there we basically go for a corresponding salt. So, the is a typical example of synthesis of metal salt, of a typical metal salt which is zinc and which is bivalent zinc, presence of bivalent zinc. So, the zinc 2 salt is directly forming, and if we add this zinc powder to a solution of this in ethanol, because if you have to dissolve this one, and we get some exothermic reaction. So, the reaction is exothermic. So, heat will be liberated by producing zinc iodide in the reaction, and since it is in the ethanol medium, so this will be in solution. So, this particular thing in ethanol solution, and this ethanol solution if we go for evaporation. So, evaporation will give rise to some white powder. So, we get a typical metal salt from the direct reaction of zinc and iodine, and is a typical example of the corresponding redox reaction. So, that is why the zinc, whether it is present in the powder form, whether it is a zinc granules or zinc rod, because this is a typical species in different electrochemical cells also, in the battery also, because zinc has the corresponding tendency to be oxidized, that means it can provide us free electrons. Similarly, what are the other species we will encounter? Not only the metallic, but the hydride transfer reagents, that we will talk next, that the hydride transfer reagents such as sodium borohydride or lithium aluminum hydride, which we use very much in organic chemistry, that basically provide not only hydrogen gas, but H minus, which is the hydride ion. So, hydride ion will transfer those electrons very easily to some organic molecules. Similarly, these hydride ions from this species is also very useful. So, hydrides are also very good reductants, and also industrially important some species which is the hydrogen gas itself. So, hydrogen gas we always require, because the gas is the reducing agent. So, gas will give us the required electron for the reduction reaction, and that gas will give rise to the corresponding electron to the system in presence of some species which are considered as the catalyst. That means, the activation of this H2 is required, because hydrogen molecule we know that it has H bond. So, activating this H2 by using palladium, platinum and nickel catalyst will be useful, and that hydrogen atoms, the activated hydrogen atoms will transfer for the, whether it is a reduction for organic chemistry or it is a reduction for the electron transfer reaction. So, this particular thing we will just see that what we have seen in terms of the corrosion, that means the corrosion is the corresponding electrochemical oxidation, that if we have something, whether you have iron in your system or the iron pipe, or you have zinc somewhere, the metallic zinc is present. So, we will definitely get corrosion, because it is degrading and it is forming zinc ion or the iron ions, because the oxidant oxygen is present in the environment. So, in case of iron or the corresponding degradation of zinc or any other metal is the corresponding rusting. So, which is common name for the formation of iron oxides, and is a typical example of a typical electrochemical corrosion. So, presence of oxygen and moisture will generally set an environmentally available electrochemical cell, and that electrochemical cell will be responsible for electron transfer reaction. So, all these reactions basically what we get for the formation of this Fe2O3, and by some chemical or electrochemical reaction. So, corrosion is a natural process what we see, and it converts a refined metal to a more chemically stable form such as oxides, what we get as the corresponding ore or minerals, or sometimes sulfides also can help, and the gradual destruction of these materials by this process by environment, that means the presence of water and the oxygen molecule, will give us a typical example of a redox reaction. Okay, thank you.